All right, good morning, everyone. My name is Colin Butler, and this is Jack Cross. We're seniors at the Virginia Military Institute, and today we'll be presenting about the design optimization and structural application of high-strength fiber-reinforced concrete. Our advisors are Dr. Ramnachano, Dr. Swinney, and Dr. D'Alessandro, who is with us here today. All right, Jack.
So yeah, this is a joint project completed at the Virginia Military Institute, or VMI, what we'll refer to it from here on out. This project was completed in two phases. So I handled the first phase, and that was the mixed development of the high-strength fiber-reinforced concrete. The point of my portion of the research was attempting to reach a UHPC compressive grade concrete of about 21.7 KSI by varying the aggregate gradations of different mixes, but still using locally sourced materials.
All right, I would then use whatever the result of his side of the research was as a laminate on a composite beam, a thin layer, either on the top or the bottom or both the top of the bottom of a normal reinforced concrete beam. I'll go over the design of those beams, how we made them, and the results from their testing.
So the proportions that you see on this slide from table 1 is Lafarge's ductile UHPC. Lafarge's ductile UHPC was able to reach a 30 KSI cubic compressive strength. They have a lot of reasons that they're able to reach this strength, like a really low water cement ratio. They used oven curing and fine aggregates, and we chose to really focus on the fine aggregates that as a big reason why the ductile UHPC was able to reach a 30 KSI compressive strength, so like much higher than the bare minimum for UHPC of 21.7 KSI. The fine aggregates used in Lafarge's ductile UHPC range from about 600 micrometers to 0.1 micrometers, so incredibly small and creates a really dense packing mixture. So again, my portion of the research, the mixed development, was focusing on these fine aggregates and figuring out a way, can I create a really strong concrete basically in my backyard. So this project is building on prior research completed at VMI in 2019. This research was done by Dr. Swinney, Dr. Ramnachano, Dr. D'Alessandro, who's here with us today, and two prior students at VMI. Their research was similar to what Colin did. They applied a high-strength fiber-reinforced concrete laminate to the different placements on a normal concrete beam and tested the beams in flexure to see how much additional force they could apply. So for the mixed development, I used their mixed proportions for their HSFRC and changed gradations with the fine aggregates used in the project with these gradations that you see at the bottom here. So the control mix was basically what they used. This was the baseline that I was trying to bolster the strength. And then there's 3 experimental mixes: the tarantula mix, which was from Dr. Lay, and the Fuller mix using the Fuller equation, and a quartz sand mix where I basically just found quartz sand and used that as the aggregate and see just what would happen to the compressive strength. This photo is from the research completed in 2019 with their the legs of Dr. Swinney right there. So these were the mixed proportions used in my mix and the research completed in 2019. It was, all these materials here were locally available except for the steel fibers, which were purchased from Dramix. Yeah, important kind of to note that some of these mixes, the quartz sand mix and the Fuller mixes, required additional, and the Fuller mix required additional water and superplasticizer, and the quartz sand mix required less superplasticizer just for proper workability when I was trying to flow these into their cubic molds. So these were the aggregate gradations used in these projects for each, the control baseline mix and the experimental mixes. The control mix was taken directly outside, just the local sand found in Lexington, Virginia, where VMI is at. The only manipulation to the control mix was removing all aggregates above the number 30 sieve and all aggregates smaller than the number 200 sieve. 200 was the smallest sieve that we had. So I mentioned earlier the ductile UHPC used 600 to 0.1 micrometers. That's about like I think it's a number 635 sieve. So it's a much smaller than the number 200 sieve. Roughly 635, but it's around that range. So the 200 again was the smallest sieve that we had. So that's what we could use. So we didn't use anything smaller than that. And the number 30 sieve was taken out because we're trying to mimic what Ductile was using with their fine aggregates, and the number 30 sieve was kind of just used as kind of coarse aggregates that wasn't going to really add to the dense mixture of the UHPC. So this is the particle size distribution for each of the aggregates used in this project. The Fuller mix was essentially the finest gradation used in this mix. And the quartz mix, being at the bottom in the yellow here, was the largest. The last slide, it showed that the quartz mix was about 97% above the number 40 sieve. So it's just number 40. The quartz sand was just a bunch of big rocks, and the Fuller mix used a lot of the really fine aggregates that was found from the sand outside. So the testing portion of the first phase of this project, we tested the static flow test and a compressive stress test. So the static flow test was kind of just done for minimum acceptability with respect to workability in the project. And the results from the static flow test showed that the quartz sand mix flowed about 16.4 and had the centimeters and had the smallest flow, and the Fuller mix had 22.65 centimeters of flow from the static flow test and had the largest flow, and all the other mixes had ranges in between there. So for this project, they were considered acceptable, and the main test with this project was the compressive stress test completed with respect to ASTM C109. For the stress test, 2 cubes were tested at 3, 7, and 28 days after a wet cure with water and saturated lime, and each mix had 3 batches, so essentially there was 6 trials for each cube. This is the results from the compressive stress test. So each bar signifies an average of 6 trials, and the order of strength that we were able to reach was from strongest to weakest was tarantula, control, quartz, and then Fuller. So this is the 95% confidence interval that I calculated for each of the mixes with respect to strength. The highest average was the tarantula mix in this third column with about 15.7 KSI, and the quartz sand mix had the highest 95% upper limit with about 17.2 KSI. So I'll just there for a second. So the results from the mix development, maximum strength that we were able to reach was a tarantula, was with the tarantula gradation of about 15.7 KSI. None of the mixes were able to reach the UHPC of 21.7 KSI with locally sourced materials, but all reached the high HSFRC category. They were strong concretes. I could tell from the research that gradations do have the effect on the concrete, but with this first phase of the project, clearly more research is needed for optimization with different maybe water cement ratios, and I have a lot of thoughts on subsequent work, but that'll be in this slide after with Colin's presenting.
All right. Next up, it's time to use that high strength concrete as a laminate. So here are the designs we used. From left to right, you have control, and then we put the laminate on the bottom, and the top, and the top and the bottom. The overall footprint of these beams was going to be was a 3.5 inch width, 7 inch depth, and 7 foot length. We had one number 4 reinforcing bar located at a 1.5 inch clear cover from the bottom of the normal concrete section, and all the laminate thicknesses were 1/2 inch. And we had 3 of each type of these beams for a total of 12. All right, moving to beam construction. The frames you see here, we used a 1/2 inch thick plywood and 2x4 sections to grate the frames. We treated them with oil before we put in the normal concrete, and then the normal concrete was sourced from a local ready-mix company and transmitted via a concrete truck. We put them in the frames, and then once they're cured, we had to surface treat the faces of the beams that the laminate would be applied to. And this was done using muriatic acid and a steel wire brush. The acid would dissolve the cement paste at the surface of the face that we desired the laminate to be applied to, and the steel wire brush was used to flick away and roughen that surface. Here's a picture of the beams before laminate application and after. All right, moving on to testing. A spreader beam with spreader supports was used to create a middle section with constant moment and no shear, just like the last presenter. This allowed us to isolate the behavior in the center of the beam and put all the shear on the outside sections. A load cell was used to measure the load applied to the spreader beam, and a wire pot was located under the beam to measure the deflection at the midspan. Here's a picture of the control beam at failure. As you can see, it fails in tension with the middle section having the most flexure cracks. All right, what was interesting, all the laminate beams failed in shear, and here's a picture of the laminate with at the bottom. Shear crack on the outside section. Here's a top beam. It's the other side of the beam, but same thing here, shear crack on the outside section. And here's the double laminate, the coolest one. All right, and here is a graphical representation of the applied load over the deflection at the midpoint for the first 4 beams we tested. That's one of each type. You'll see the top bottom beam is above all the rest in terms of ultimate strength. And the control beam actually outperforms the single laminate beams, which is surprising, but we believe that's due to a lack of shear reinforcement. It can also be observed that the most ductility happens, or the most ductility is observed through on the composite beams with top laminates, and the bottom beam without a top, or a bottom laminate without a top laminate actually lowers the amount of ductility seen. All right, so we believe that the single laminate beams underperformed because the initial design we designed for was actually a 1/4 inch laminate on our beams rather than a 1/2 inch, and that ended up being very impractical to actually make because the 1/4 inch laminate of this very, in general, low workability mix was very hard to actually apply precisely, so we ended up getting about 1/4 of an inch after we took the frames off, which means that we should have put shear reinforcement in, even though the initial calculation said otherwise. All right.
Yeah, so this is what I was kind of alluding to when I was speaking. So future recommendations. So again, this was really an initial phase of this project. So first was a petrographic analysis of the concrete. So this is what we wanted to complete, but kind of running out of time with the semester ending. But we were hoping to take a petrograph analysis of each sample and calculate how much air voids was within each of the mixes to see basically how much was each mix able to pack and decrease the air voids, and then correlate to the resultant compressive strength as to why certain mixes were stronger than others. Additionally, we wanted to do some more material property tests like the tensile strength test, modulus elasticity, and the Poisson ratio to just garner further information on the other samples. The Fuller model, I think, warranted further inspection. This used the finest aggregate, so my thinking was it was going to have the densest packing and the highest compressive strength, but it was actually the weakest. I believe it needed further optimization with the water cement ratio because it did need more water so that I could pour it into the cubic molds. And different aggregate combinations, so ductile UHPC combines silica fume with crushed quartz and their fine sand aggregates, and I think this could be another element to reach a UHPC compressive grade concrete locally.
Like I stated before, if we added shear reinforcement, we'd be able to see that increased moment capacity that we calculated for, demonstrated during the tests. For future recommendations on this side of the research, I recommend, instead of focusing on the location of that laminate like this project did, you vary that thickness, find that optimal UHPC thickness, and this time you use commercially provided UHPC. That way you know exactly what that mix you're using is. It's not so experimental like in this case. And here's some of the people that helped us out during our project. All right, are there any questions? Thank you. Yes, sir.
The laminate thickness that you're using is very thin, given that you're using steel fibers, and that seems like it might be too thin for the fibers to be placed well.
Yes, sir. How big were our fibers? They're a real thin. I would say.
Length and I think 0.28 diameter.
Yeah, but if they're like half-inch long and you're doing a half-inch overlay,
I believe they're about like a quarter to maybe a little bit half of that thickness. But you're right. Thank you very much, sir. Maybe increasing that thickness could allow for those steel fibers to be used more versatility.
Thank you. Any other questions?
I thought this was very interesting research. I was curious where you see like the application of this laminate being applied.
Okay, so when we were doing that initial research, that background research for this project, we found that a lot of applications for UHPC right now is actually applying a thin layer to the top of a bridge deck as a remedial treatment to that bridge deck when it's starting to degrade on the surface. So we were like, okay, perhaps we can do a top layer on a beam to see if it increases that moment capacity. It's kind of a tangential application of that. But yeah, we just wanted to see an efficient way to use this really hard to use material.
Thank you.
Thank you.
Is that all? Yeah. Thank you, everybody.